There's the sun.
Pretty hot.
Yeah, it is.
Pretty sexy. Looks pretty sexy.
The sun, compared to all the planets, is huge.
Really cool.
It's almost 1,000 times the mass of all the planets combined. Makes up 99.8% of all the mass in the solar system. So, if you think about it, the way the solar system formed, it was a giant spinning ball of gas and dust that fell in on itself to make the solar system. Did we already talk about that, how the solar system formed?
Yeah.
It was like a big bang, right?
Well, no, that's the universe.
He said something happened and it started whipping around.
A big gas cloud contracted and started spinning and eventually formed all of our planets and the sun. But the sun is at the very center of this big gas cloud, so that's where most of the stuff ends up, in the middle, because gravity pulls it to the middle. So you have this giant ball of gas just being compressed in the center of the solar system, and that ended up being the sun. It's way more stuff in the middle than there is out on the edges where the planets are. It's hydrogen and helium, just like the gas giants. 75% hydrogen, 25% helium. It's got a higher percentage of helium than the gas giants does, because inside the sun, the hydrogen is converted into helium through a process called fusion. Have you ever heard of nuclear fusion before? This bomb right here is a nuclear fusion bomb.
Dang.
And it's
Where is that?
it's at Bikini Atoll in the South Pacific.
Where my marine bio people at? Yeah.
There you go.
I know how Atoll is.
And they wanted to see what kind of damage it would do. They just invented those bombs.
Coral Atoll.
And so they had a bunch of captured ships from World War II, and they set it at different distances and put the bomb right in the middle.
Oh, okay.
And they blew it up, and that was filmed from a remote camera nearby. And what is actually happening there is the bomb has hydrogen in the middle of it. It's what's called an H-bomb or a hydrogen bomb. And what they do is they set off a nuclear explosion, an atom bomb, like the kind they dropped on Hiroshima. They set that off near the hydrogen, and it gets so hot that it fuses the hydrogen. And when hydrogen fuses with other hydrogen, basically the hydrogen atoms connect to one another, and they form helium. And that gives off a lot of energy when that happens. The process of fusion gives off a lot of energy, and that's why you get a giant explosion. In that giant explosion, that's just a little bit of hydrogen being converted into helium. Inside the sun, it's a lot of hydrogen converted to helium. Somebody did the calculation, and it's something like 100 billion hydrogen bombs going off per second in the center of the sun. Yeah.
So at one point, will the sun be 100% helium?
It will be, but it'll actually blow up before it gets to that. We're going to go through the process of stages in the life of a star. But the star will live for about 10, a star the size of our sun will go for about 10 billion years converting hydrogen into helium. But then it starts to run out of hydrogen, and it starts to sputter a bit, kind of like a car running out of gas. And then it'll start fusing helium, but at that point the star's dying, and it starts getting bigger and bigger, and it goes from a star like our sun to a real big star called a red giant. And then some stars, if they're even bigger, they'll do other things like collapse and explode and do these things called supernovas and stuff. We're going to learn about all that coming up. So that's what happens when a star dies. It's used up its hydrogen fuel and starts to burn helium and other stuff, and it starts to get weird. Yeah.
Aren't the gas giants hydrogen?
Yes. So the gas giants would become stars if they were big enough. So what you need to become a star is enough gravity to pull that hydrogen in tight enough where it fuses at the center. Now Jupiter's our biggest gas giant, and it doesn't have enough gravity to do that. So the center just gets pulled, a lot of stuff gets pulled in, and it ends up forming this rocky core. But if Jupiter were about 80 times as heavy as it is, it would have so much gravity that it would pull in that hydrogen, and the hydrogen would fuse at the core, and it would become a star. And we would have another star where Jupiter is. But it's not that big. And you see that on a lot of star systems. You see double stars, two stars kind of going around one another in a little dance.
How big is Jupiter compared to our sun?
Jupiter is 1/500th or something like that, the size of our sun. It's a lot smaller. Sun's big.
Does the sun have a Roche limit on it? Like, does that
It
apply to
does.
this too?
It does.
That's Jupiter.
So I don't know if it's the same for the sun, but I would guess it's about 2.4 times the radius of the sun. Does it say in the reading what the radius of the sun is? Did I have that on there? How big it actually is?
The radius? No.
It's not in there? Google that. Radius of the sun. Siri could probably tell you.
It's 432,288 miles.
So 432,000 miles radius. That means it's 860,000 miles wide. So to give you some perspective, the Earth is 8,000 miles wide, I think. The Earth is 8,000 miles wide. And I think Jupiter's 80,000 miles wide. So you can fit 10 Jupiters across into the sun. But of course, by volume, that's like 1,000 Jupiters inside the sun. So, sun's big. Did I mention the sun was big?
Yeah.
Did you know the sun spins around? Most people don't know that. The sun rotates, just like all the planets rotate on their axis. We know the sun rotates. You can see it because you can see the sunspots moving around. You see those little dots on the sun? Those are called sunspots. And what sunspots are areas of the sun that are actually cooler than other areas. And there's a reason why they're cooler. It's because of the sun's magnetic field. The sun's magnetic field moves in and out of the sun and moves gas around. And points where the magnetic field comes up out of the sun and goes back into the sun are cooler. And so those spots are cooler spots. Now when I say cooler, that's cooler than the rest of the surface of the sun. The surface of the sun is about 6,700 degrees Celsius, which is hot. The sunspots are about 4,000 degrees Celsius, which is cooler than the rest of the sun. But 4,000 degrees Celsius is hot. So if you were to touch a sunspot, it would burn your hand up. It's just cooler than the rest of the sun, and that's why it looks dark. Now, if you were just looking at a sunspot, it would be real bright. What they've done to be able to see the sunspots is they've put filters over the lens. It's like wearing sunglasses. If you wore enough think about it, if you wore enough pairs of sunglasses, if you stack sunglasses on top of sunglasses, eventually it would get so dark where you could look right at the sun, right? And if that was the case, you would see these areas where the sunspots are. They would be darker than the rest of the sun because they're cooler, and they would appear as spots. So this picture is taken with filters over the telescope. Yeah.
Could like a human eye see that from Earth with a bunch of sun?
No, they're too small. but you can see it with a telescope that has a filter on it. I have telescopes, and I've got solar filters. So we're going to go out there and look at the sun the next time the sun is up during class. Not right now, because it's early and cloudy. Just remind me, next time, if we come in tomorrow and the sun is out, we're going to go look at it with the telescope and the filter. And you ought to be able to see these sunspots. They won't be moving fast like this because it's sped up. The sun rotates once every 25 days. So it takes 25 days for the sun to circle around once. But that's at the equator. It takes 31 days to go around at the poles. We call that differential rotation. Can you say differential rotation?
Differential rotation.
That means the middle is rotating at a different speed than the poles. And this happens in our gas giants. The gas giants were like that. I don't think we talked about it. But the gas giants have a differential rotation too. They rotate faster in some areas and slower in some areas. And so does the sun. Faster at the equator than at the poles. And you can do that if you're a gas planet. You can't do that if you're a solid planet like the Earth. You have to rotate all because it's all connected. But if you're gases, the middle gases can be going faster than the gases at the poles. Isn't that cool?
Crazy.
And the fact, this differential rotation is important because the fact that the middle goes faster than the poles causes the magnetic field to get all twisted up, which we're going to talk about in a minute. Here are the sun's layers, and this is what you have to know from this chapter. Let's memorize them now. Let's not wait till later and go, I'll memorize that later. It starts with the core in the middle. That's where the fusion is happening, in the core. Then you have this zone called the radiative zone. That's this zone outside the core. And the radiative zone is where radiation comes off the core and flies out in all directions. And you would get irradiated if you were in that. Most of it's gamma radiation. You ever heard of gamma rays? Remember those ones that are vibrating the fastest? That's because the core is at 14 million degrees Celsius, something like that. And anything that hot is vibrating so fast it produces gamma rays. And the gamma rays shoot off in all directions. Now we're lucky those gamma rays don't come right out of the sun and hit the earth or we'd all be fried. But what happens is the gamma rays shoot through the radiative zone and then they hit this area called the convection zone. And the convection zone is actually cool enough where the atoms can absorb, it's hydrogen and helium gas, they can absorb this radiation. The gases absorb the radiation and heat up. And then the gases in the convection zone rise as they heat up. Yeah, have you all heard of convection, the process of convection? Convection is what you see going on in a pot of boiling water. Hot material rises.
Isn't that why you have to like crawl when there's like fire?
You have to do what?
You have to like crawl when there's a fire on the ground.
Because higher up? Yeah, that's a good point. In a boiling water, the heat's coming from the bottom. The hot water rises, and it gets to the top, and it gives off a lot of the heat, and it cools off, and then it falls back down. And you just get this rolling going on inside the pot of boiling water. The same thing's happening in the convection zone of the sun, except it's not water, it's hydrogen and helium gas. They absorb the radiation, and the gases rise up and cool off and then fall back down. Rise up and cool off and fall back down. That's the convection zone. And believe it or not, it's a lot cooler by the time this stuff gets to the top. It's a lot cooler than it was way down here. And when I say cool, that's a relative term. It wouldn't be cold like you would be in there going, ooh, this is freezing up here. It's still thousands of degrees. But it cools all the way down from millions of degrees in here to thousands of degrees up here at the top. And then you reach what's called the photosphere. That's the next layer. The photosphere is where the light is given off from the sun. So the photosphere is about, I think it's 5,700 degrees Celsius. And that's at the top of the convection zone when the material comes out and it's yellow hot. Do y'all remember when we did all the different colors? You had red was the coolest visible. Remember Roy G. Biv?
Yeah.
So, our sun's energy peaks in the yellow portion of the spectrum. So, actually more like this. Well, y'all remember the, what was it called, the curve? The,
Bell curve.
not a bell curve.
It was, oh.
It was the black body curve. Remember the black body curve for the sun? Peaks in the yellow part of the spectrum. Yellow's at about 5,700 degrees. And that's the temperature of the photosphere. And so yellow light is given off the most. And that comes shooting out of the photosphere. But actually all colors are somewhat represented. It just peaks in the yellow. All colors are represented to some extent. And that's why you kind of see white coming off the sun. But if you analyze the light close enough, you'd see there's more yellow than anything. Yeah?
Do you have to have an atmosphere to absorb the heat from the sun?
You mean on Earth?
Well, like, you know, in Apollo 13, when they had to like turn the electricity off and everything, and it gets really, really cold in there.
Yeah.
Like, why is it cold in there if that's the same distance as the Earth to the sun?
Yeah, that's a good question. If in the spacecraft, I guess that the radiation is probably just bouncing off the spacecraft, and there's nothing to absorb it. It's probably shielded from heat getting in from the outside. And so I guess that there's no way to transfer that heat energy into the spacecraft. They have their own system for keeping the temperature inside the same. And the answer is no. You can, if you had something to absorb that heat, you could use that sun to heat up the spacecraft. So I'm not exactly sure how the spaceship works. For some reason, when they turned off the energy, the system got cold. But I know, like on the moon, there's no atmosphere, and when they're in the sun, it's real hot, and when they're in the shade, it's real cold.
Okay.
I don't know if the way the spacecraft is built, it's all the sunlight's just bouncing off of it, and they're not absorbing any heat. I'm not exactly sure how that works. It's a good question. Have to ask someone who knows about spacecraft. Okay, so that's the photosphere. Is the part of the sun, and light just shoots off the photosphere and comes to Earth. Now, above the photosphere, and so when we look at the sun, we're seeing the photosphere. That's the brightest part. That's where most of the light comes from. Above the photosphere, there's a couple more layers that are thinner and give off light, but they don't give off nearly as much, so you can't really see them when you're looking at the sun. It's called the chromosphere. It's kind of a red area, and gives off some red light, and there's material that rises up into the chromosphere from the photosphere and falls back down. And then there's the corona, which is a very wispy area of gas above the chromosphere that is whipped around by the magnetism of the sun, and is very, very hot. The corona is actually millions of degrees. but it's so thin you can't see it very well, and it sticks out beyond the sun. You can see the corona only during an eclipse, and where the sun is blocked by the moon, and then you can see the corona out on the edges. Otherwise, the sun is too bright to actually see the corona sticking out. So those are the layers. Do you got them memorized? Let's try and memorize it right now. You ready?
Okay.
Core in the middle.
Core.
That's easy enough, right? Like the core of an apple. And then the radiative zone, that's where the radiation comes shooting out. And then the convection zone, that's where the material rises and falls back down like boiling water. And then the photosphere. And then the chromosphere. And then the corona.
Too bad.
Is there an acronym term?
Yeah, I was just gonna ask that.
I don't know. Can you invent one?
Can you write it down first? Extra points.
One problem is you got a bunch of them starting with the letter C.
Yeah.
Core, convection, chromosphere, corona.
Coronal hole.
Coronal hole? Huh?
Coronal hole? What did I say?
Coronal hole?
Yeah.
Oh, that's an area in the corona
What is
where
that?
there's nothing. We'll talk about those in a little.
Okay.
Actually, we'll talk about those
What
tomorrow.
about the flares? Is that like
Flares we'll talk about tomorrow. Those are things that fly off the sun and release a lot of energy. These are all the flares and the coronal holes and the prominence and the sunspots. Those are surface features of the sun. That's tomorrow's chapter. Okay, so 5 points each. If you can memorize, if you can write down the 6 areas of the... what's wrong with it?
Should I pause it or
No, don't pause it. Let it go. Will it not stay on the thing?
no?
5 points each for the layers of the sun.
Yep, it's good.
Hold on, let me see this.
It's just really difficult to keep it on there.
I think if you
Okay.
just it will fall if you knock it,
Yeah.
but if you don't, it should be fine.
Wait, how many do you want us to write?
Each layer of the sun, 5 points each.
All 4 of
Too
them.
bad handwriting on it.
Yeah.
Yes. Green, all 6.
Yeah.
There's 6 layers.
Oh jeez.
Did you knock it off?
Yeah, I did.
I shouldn't have set it up for you. All 6 for Peach.
Good work, Charlie.
Anyone else?
We try to write it.
Sure.
I don't want to.
White. All 6. Blue. All 6. Orange. Weren't you glad I didn't say banana?
Banana, huh?
Uh-oh.
Joke.
Oh. Only 4.
Are you serious?
Okay, so one more time.
Down.
Core,
Core.
radiative, convection, photosphere, chromosphere, corona. Got it?
Yeah.
Okay, so how do we know what's going on at the core? This thing is called a neutrino detector. And scientists know that if what's going on in the core is what they think is going on in the core, tiny particles called neutrinos should be emitted from the core of the sun. The cool thing about neutrinos is they're almost massless particles that do not react with matter very easily. And they fly off in all directions from the sun by the trillions. And they go right through the sun. And they go right through the earth. There are trillions of them passing through your body right now, neutrinos. And they don't react with anything. They just go on through. They have just a tiny bit of mass. They're hard to tell they even exist. But if you have one of these, which you don't have because it's incredibly expensive, there's a man standing right there if you're wondering how big it is. That's another man.
Wow.
This is a giant neutrino detector that you have to put real deep under the earth away from any other radiation source. And for every billion, trillion neutrinos that pass through this detector, one will react with the water that's in the detector. It's got a special kind of water that's in the middle. It's called heavy water. It has a certain type of hydrogen. It's heavy hydrogen. And anyway, neutrino will react with that water, and it'll release a little flash of light if that happens. And that's the only time these things release a little flash of light, if the neutrino reacts with the water.
So it's like a giant.
And so all these little dots on the outside are light detectors looking inside for a flash of light. And theory predicts that if what is going on in the sun is correct, there should be 10 flashes of light per year inside that detector. Or a certain number. 11 flashes or 7 flashes or something like that. And so they measure the amount of flashes and see if their theories about what's going on in the center of the sun are correct. That thing costs hundreds of millions of dollars to build. There's only a couple of them in the world. I think that one's in Japan.
They could go months with no flashes.
They could, yeah.
Wait, so what's the
And actually, I think they built it and they went a few years without flashes, and we're wondering if the dang thing was working. But once they got it settled and fixed, they started getting the flashes that they predicted, and they actually know from these things that what's going on in the sun is what theory predicts.
How deep underground are they?
What's that?
How deep underground are they?
It's deep. That's a good question. It's hundreds of feet deep, way down. As deep as it's in an old abandoned mine, where they've dug down into the ground to dig out rocks and metals and stuff, and they put this thing in there. This is a cool picture. This shows the granulation. Remember the convection zone?
Yeah.
Remember I said it's like boiling water that bubbles up. This hydrogen gas bubbles up and then falls back down. This is using a big telescope to look at the sun. You can see these areas of where the boiling water comes up and falls back down. And just to show you how large it is, that's how big the North America would be compared to these granulation bubbles on the sun. These things are huge. And so we call this solar granulation. It's evidence. And they have video footage of it. This is basically the sun boiling. It's a very cool video.
The surface.
The surface of the sun boiling. If you could see this, if you had a good enough telescope. And again, the size of the United States is about the size of one of these bubbles.
Crazy.
You said this is real?
Yeah, that's real video footage.
No, it's fake.
Taken, of course, with the camera that has a filter on it, so it's not so bright. That's what the surface of the sun would look like if you could see it.
What color would it actually be? For it to be
It would be yellow. White, yellow.
Is the center of the sun violet?
Yeah, it would be blue. Because it's so hot.
Is there any solid part of the sun?
No.
Great question, Alistair.
No solid
Team
part of
blue.
the sun.
And no liquid part.
No liquid, no. It's all gas and plasma. Have you ever heard of plasma?
Yeah.
Mhm.
If you get a material hot enough, the electrons come away from the atom. And you're just left with protons and electrons kind of floating all around everywhere, not attached to an atom. We call that plasma, and that's what the sun's made of. A plasma TV screen
Yeah.
has a glass container, and in the middle is hot gas that is so hot it forms plasma. And plasma computer screens were like that too, and most of them use LEDs now, but it's a little different, but that stuff in a plasma TV screen was as hot as the sun. I mean, we can get temperatures as hot as the sun. A light bulb that produces white light is just as hot as the surface of the sun. Now, it's hotter on the inside of the sun than any of this is. But the outside of the sun, people don't understand. They think that the sun is the hottest thing. The outside of the sun is no hotter than a light that's producing white light, because the sun is producing yellow light, and that's how hot it is on the outside. You go inside the sun, and that's where it's really hot.
So could you fly right up next to the sun?
No,
Why not?
You would die.
because it's so hot. It's still, even though it's no hotter than a light bulb, it's big, and a lot of heat is coming off of it. If we made that light bulb real big, so much heat would come off of it that it would fry it. Yes?
What did you say the purpose of that big underground ball thing was?
To detect neutrinos. That's a neutrino detector. Neutrinos fly out of the core of the sun. That's really the only evidence that makes it here unchanged from the nuclear reactions that are happening in the sun. There's a bunch of gamma radiation too flying out of there, but that hits the rest of the stuff and comes out as light. We don't see what's going on in the sun directly, except for the neutrinos that come out of it. Yes?
How do you learn plasma later? Isn't it like one of the four solid?
Yes,
gas?
solid, liquid, gas, and plasma. If gas is heated up so high, the electrons will come off the atoms, and you'll be left with plasma. There's a picture of the chromosphere. It's a little cooler than the photosphere. Red. A little thinner, so we don't see it as well. And then there's the corona. Remember I said if there's an eclipse, you can see the corona? This is an eclipse. And you can see the red part you see there, that's the chromosphere. It's a great picture. And that part right there is the corona. And it's so thin that we can't see it when you look at the sun, because the rest of the sun is so bright. But if you block out the rest of the sun, you can see the corona. That's right now the sun has that on the outside of it. It's like a hairy sun. Isn't that cool? And that stuff, the corona, like I say, is really hot. That's hotter than the surface of the sun by a lot. But it's so thin that you can't see it very well. So here's a picture: photosphere, chromosphere, and then here's where the chromosphere starts to transition into the corona. Here's the corona out here. The last thing in the reading is about solar magnetism. And do you remember I said the center of the sun spins faster than the poles? You remember that?
Yes.
What this ends up doing is twisting up the magnetic field of the sun and causing all these issues that we're going to study tomorrow on the surface of the sun. And this is a video of how that twisting occurs. Watch the sun get all twisted up here.
This video clip reveals the links between sunspots, magnetism, and activity in the sun's million-degree outer atmosphere. The images were obtained with the 1 megapixel cameras on the ESA-NASA SOHO satellite and the NASA TRACE satellite. We begin with images of the visible surface of the sun. These show sunspots as darker patches. A special filter reveals the sun's magnetism in black and white. The strongest magnetic elements are found in sunspots, but the entire surface is covered with a salt and pepper pattern in constant motion. Another filter reveals superhot gas. This gas is trapped in magnetic loops above the surface of the sun. Zooming in on these loops reveals a continuous flickering. This activity is produced by the shuffling about of the magnetic elements on the surface.
So that you see there, those are little magnetic field lines, like we have on the Earth. We're going to study